Okay, everyone, let's start our first pre-lecture video for today, where I'm going to wrap up one of those topics that we ended up talking about last Wednesday, about validation and how you select the right model complexity using this other technique called cross-validation. And then I'll launch us into our discussion for today's topic of this thing called regularization, another way of trying to prevent overfitting. But in this video, I'm going to focus on recapping this idea of a validation set and then introducing this other algorithm called cross-validation. So last time, we were settling with the problem of discussing different model complexities from very not complex to very complex models and how that ranges and trade-off in their bias and variance, which both contribute to the error just like the noise does. And we are asking the question, how do we choose the right model complexity? And we came up with an intuitive but wrong answer of choosing the one that minimized error on the test set. And while that's exactly right, you'd want that to be right, it has the right intent, it ruins the idea of the test set being this standalone thing that represents all future data. Because if we choose the model that does best on that one particular test set, it's no longer a good estimate of future performance because we chose the model based on that one particular test set. So we were trying to explore other ways. Like, we know we can't use the training error because that would select for overfit models. And the test error is right in theory or the right intuition, but it's not exactly what we want to practice because it ruins the point of the test set. So we said that there are actually two other ways of trying to assess a model in terms of finding the right complexity. One is using a validation set, which we covered on Wednesday. And then what I'm going to talk a little bit about today is doing this other procedure called cross-validation. So as a quick reminder, let me remind you what using a validation set means. The idea being that in the old world, we split up our data into train and test, train to train on, test to test our model at the end to get a good assessment of how it will do in the future. Well, we wanted to potentially use the test set to choose the right model complexity to get the best model that will perform well in the future, but then it ruins the point of the test set being held out because we chose the model based on that test set. So the trick is just use another data set. So split up your training set even further into train, validation, and test. Train still has the same meaning as before. Test still has the same meaning as before. But now this new set that you make, the validation set, you use to choose the right model complexity. So you search over all your model complexities, assessing them on the validation set. And so that gives you an estimate for which model will do the best in the future without biasing yourself towards the test set in particular. And so at the very end of this validation procedure, you can now use that test set that you have not touched or made any decisions about at all. You've just used the validation set. So the way that this algorithm works or looks like is you start by splitting up your data into train, test, and validation. And then for each model complexity you're interested in trying, train a model on train, validate it with the validation set, and then keep track of the degree polynomial p that has minimized the validation error. This will prevent you from picking models that are overfit, because overfit models probably won't do well on the validation set. But now you aren't biasing yourself towards your one particular test set. At the end, you can now test yourself on test and report your error as an estimate of future performance, because you've never looked at that test now. So it's similar in theory or in the idea of trying to test yourself on another data set, but it can't be your test set. You got to keep that till the very end so you can have an accurate prediction of future error. Now, validation sets are great. They're very easy to describe and implement. Like, it's just the same idea as a train test split. You just need another split for validation. And it's a relatively fast procedure. You still have to train a model for each of the complexity or each complexity you want to use, but that's going to be kind of unavoidable. You're going to have to train all the models to try them out. And you only have to evaluate each model on the validation set once. The con to this is you might kind of saw in that earlier picture where you split up train even further that you're making smaller and smaller training sets now. because you have to cut away even more data. So you're losing data to train on, which is never necessarily a good thing, but it's going to a good cause for validation. And so what I want to introduce in the remainder of this video is another approach that can kind of fix this con, so you don't have to give up more data. And the idea is we're going to use this thing called cross-validation. We're going to talk about this other type of algorithm that kind of uses a slightly different approach to estimate model performance in the future. So here's the big overall clever idea for cross-validation. Instead of making one validation set, we make many small validation sets so we don't lose too much training data. So we still need to break off our test set like before. You need to do that. The first things first, split your data into a test set and keep that aside and never touch it till the very end. But after we do that, we're going to have our training set. And instead of just breaking it into train and validation, we're going to break it into K chunks. So K is a number you have to pick. We'll talk a little bit about that. So let's just suppose I want to use 4 chunks. I break my training data into quarters. So I'll have 4 chunks. Then the idea is we're going to kind of repeatedly train a model, leaving one chunk out as a time and using that one chunk as part of our validation set. So the idea is we're going to pick a number K, how many chunks we want. And then we're going to train a model K times, each time leaving one chunk out, training on the rest, and then assessing ourselves on that left out chunk. So the way this kind of looks in pseudocode, looks a little bit more complex, is we split our data into test and our K chunks. And then like before, for each model complexity, so for each degree polynomial or whatever other measure of model complexity we use, we're then going to loop K times, and we're going to train the model on all of the chunks except the ith chunk, where I is our for loop variable, starting at 1, then 2, then 3, all the way up to K. So we hold out one chunk, and then to assess the model, we assess it on chunk I. And then we've done this K times. So for one model complexity, degree 4, we train K predictors of that model complexity, each one withholding one chunk. And then we find their validation accuracies using each one of those chunks, and then average all of those up. And then keep track of the degree polynomial P that has the lowest average validation error across these K chunks. And then like before, you could still test it at the very end with your test set. So similar to the idea of a validation set as before, but now we break our whole data set down into K chunks, and we train K models, leaving one chunk out at a time. So you might be wondering, this just sounds a lot more complicated than using a validation set. So why might we use this? The nice thing is that you don't have to actually get rid of any training data. That at the end of, or at least if you make K large enough, or that means each chunk is going to be small, the amount of data you're withholding is minimal. That if I'm using K is equal to 100, I'm breaking my data set into 100 chunks, the one chunk I leave out is a very minimal part of my data set. Unfortunately, this doesn't come for free. This approach could be quite slow because we have to have this loop that goes over all model complexities. And then for each model complexity, it has to train K different models. And you might be wondering, well, okay, what's the right level of K to choose? Do I want a few large chunks or many small chunks? And it turns out for the best result, you need K to be as large as possible. So theoretically, the best estimator is to use K is equal to N, meaning your chunks are each going to only have one data point in them. We sometimes call this leave one out cross-validation. If you use K equal to N, the number of training points, that means you're going to train one model for every data point in the data set being left out once. If you have 100 data points and you use K is equal to 100, each chunk will have one value in it, or one data point, which means when you go to train each of the 100 models, you just leave out one example and then test on that example. And it turns out that's the theoretically best setting of K when you're working with cross-validation. Is this leave one out cross-validation gives you the best estimate of future performance. Unfortunately, using k is equal to n is quite expensive to compute for very large data sets with only with 1,000 rows. That's not very a large data set, but that means you have to train 1,000 models for each model complexity. That's way too much. So in practice, people tend to use something like k is equal to 5 or 10. It's some middle ground between making leave one out cross-validation, if you possibly could, to doing something like just leaving out a validation set. So this is a nice middle ground that lets you kind of tune how much validation you want, which is a very useful thing to be able to do. Whenever you're able to tune things with knobs or levers in machine learning, it can be very helpful because it gives you control over the process, that you can choose what things you value. Do you value time, or do you value very good estimates? So as a quick recap of everything we saw last Wednesday and what I just introduced now, the theme here was trying to assess the performance of our models. So we talked about model complexity last time, and the idea of having a train error and a test error, and this idea of true error, what the model will actually experience out in the real world, even though we don't have access to all future data. We talked about the ideas of overfitting and underfitting, and we talked about how overfitting and underfitting come from this bias variance trade-off. And how, when we talk about things like model complexity, those are with respect to how much data you have. Generally, more data is better because it gives you a more representative sample of the world, or at least hopefully gives you a better representative. And then we showed you two ways to settle on choosing which model complexity you want, either using a validation set or a cross-validation. Both of them have the same idea of you want to test your model on something it hasn't trained on, and they just take slightly different approaches of making a new data set to test on. That's not your test set because you need to leave that aside. So these are all great techniques and ideas that will underlie a lot of the things we'll be talking about the remainder of this week. We're going to talk about this thing called regularization, try to help you prevent overfitting with a slightly different knob you'll turn. And so we'll introduce that in class today. But what I'll start with in the next video is talking about some background information about kind of where this idea of regularization is coming from, what's it's trying to control for. But we'll approach that in our next video.